Hello. I am so happy to welcome you on the third part of the chemometrics course here at Stockholm University on spring 2022. And I'm first of all very sorry that we can't meet today in person and that I have to give this introduction to you over a Zoom video. So I'm very sorry. But there are good reasons to having this online instead. And in this part, over the next couple of weeks, we are going to dig into now multivariate analysis. So you have been during this course already looking at the basic statistics in the first part, and then in the second part you actually came already closer to multivariate analysis. You were optimizing with different methods, different strategies, and you already actually had a bit of multivariate analysis as well. But here in this part, we are going to really dig deeper into that and see how this really works, multivariate statistics in practice. And we are going to show here and demonstrate here some of the really novel methods that are used in treating multivariate data. So why am I giving to you this third part of the course? So by training, I'm a chemist like all of you. So I graduated in 2010 from PhD, and my thesis was focused on liquid chromatography mass spectrometry. But during my studies, I really became very keen about data analysis. So I understood that it's very important to dig deep into the data that we obtain with our chromatographic and mass spectrometric analysis. So first I digged into the statistic parts. So I actually started then teaching the basic statistics, and also a year later I started teaching the multivariate analysis part when I was in my PhD in University of Tartu. Then years went by and my research increasingly was using data, and we started doing modeling to understand what is going on in our analysis when we were doing our environmental and food LC-MS analysis. And a couple of years ago, I understood that I need some more education. So I went back to university and I completed additionally master's studies on IT. And there my focus of my master thesis there was to develop with machine learning models in the computer derivatization reagent that would improve detection limits in liquid chromatography mass spectrometry. So not doing it synthetically, but doing this synthesis in the computer to figure out how to do the analysis in the best way. And this is very close to the optimization that you have been having in the second part of the course, but I use more multivariate machine learning strategies for that. Yeah, so from this, I also have a bit of training as on the machine learning and multivariate part, not only as a chemist, but also from computer scientist's point of view. And my research group is also blending two fields, analytical chemistry and machine learning. So we are all by training analytical chemists or chemists, and we additionally have some background in machine learning. We have learned that in some courses. We try to really apply this to make the best use of data in analytical chemistry to make best decisions, best predictions, and to understand what is going on in the methods that we are using in analytical chemistry. So I'm very excited to share these experiences with you, and I really hope that you get best out of this, and that you can also use this later in your career. So maybe from the career point of view, I would also like to mention that being able to use multivariate statistics and especially machine learning has become really, really important over the last 5 years in the job market. So today, analytical chemists do not only operate instruments and extract samples, but they also look at big data and finding patterns and information from this big data can't be done manually by scrolling through Excel sheets anymore. For this, knowing the multivariate analysis and machine learning tools is the key. So more analytical chemists increasingly need this in their daily jobs. And this not only if you're more R&D, working on R&D, but also if you're working in regulatory laboratories. So for example, currently we have a nice collaboration with Svensk Livsmedelsverket, who is applying non-targeted screening with liquid chromatography mass spectrometry for different samples. And looking into this data really requires good grasp of multivariate analysis. So even in regulatory institutions, this is very, very important. And I can also comment that out of the students who have graduated from my group, many are actually working in mass spectrometry, but many are working also on the data side of the chemists. So many of them are doing actually softwares for chemists or data solutions for chemists, and some of them do them both in some laboratories. So now you want to maybe ask, why do we learn multivariate analysis? Why is this important to us? And generally, multivariate analysis come to rescue in research for two reasons. First, when we want to understand something, and secondly, when we want to predict. So generally we can say that research is either about understanding or predicting, and multivariate analysis really helps in both of them. So for example, when you look at a retention in chromatography that you all have learned and used before, so the understanding could be, why does one of my analytes retain stronger than the other of my analytes? What's the difference in their structure that actually is causing this difference in retention? And this is something where multivariate analysis can help us answer the question. But also, for example, in non-targeted analysis, we often want to predict retention times for candidate structures. And then we are asking, what could be a retention time of this structure if this was in my sample? And this is again what multivariate analysis can help us to do. So it can both help us to understand what is going on, but also to predict. These tasks are a bit different, and we need to choose suitable methods depending on what is the task, but both of them are strongly relying on multivariate analysis. So the two main techniques that we are using in multivariate analysis and that we will be looking very much here is regression and classification. So in regressions, we are trying to predict or model for understanding a continuous variable. This means, for example, retention time that can be any value between dead time to the end of the gradient. So it's a constant variable. But we also look into classification tasks. This is, for example, that we have a blood sample, and we would like to know if this blood sample is belonging to a person who has a specific disease or who doesn't have a specific disease. So based on the blood sample and the analysis done from this blood sample, maybe some chromatographic analysis, maybe some spectrometric analysis, maybe something else, we want to be able to predict if this person has a specific disease. Or if we have a question, we can also formulate this question more on the understanding point of view. Sometimes from the blood sample, we have analyzed a specific set of metabolites, and we would like to know what metabolites are actually associated with the disease. So which metabolites are upregulated and which are downregulated. And we will be actually looking very much into both these kinds of tasks, and we will have both cases about retention time as well as diseases and how this is related to metabolites and how metabolites can predict diseases with multivariate methods. So we'll be covering this in this course. So some of the examples where multivariate analysis can come handy in chemistry and in analytical chemistry particularly. So first of all, retention times, of course. Analyte properties that are related or can be related to retention times are manifold. So we have, of course, polarity, we have acid-base properties, we have polarizability, hydrogen bonding, flatness of the structure, and so on and so on. But also system properties. So what kind of a column we are using, what type of a chromatography it is, what is the solvent, what is the pH, what puffer type, what organic modifier. So from this, and all this plays role in the retention. So from here, we see that this really is multiple parameters that are affecting retention time. So this is what it means, multivariate analysis. We have very many properties that are important, both for analyte and for the chromatography system. And we need to take them all into account to predict and understand what the retention time of a chemical is actually, is and why it is what it is. So multiple parameters. Or when we are trying to evaluate kaolinite content in paper for paper conservation, kaolinite is a chemical that has actually a fairly nice impact on the infrared spectrum due to the carbon-oxygen bonds, and kaolinite can be quantified from the IR spectrum. But in IR spectrum, it's not only, of course, the kaolinite that is giving signal. Also, other contents in the paper are giving signals in IR spectrum. So when we try to quantify it, we need to take into account the whole IR spectrum. And when you think about it, when you have a IR spectrum measured from 400 reverse centimeters to maybe 4,000 reverse centimeters with a resolution of 1 reverse centimeter, then there are more than 3,000 variables there that need to be taken into account. So how to manage such large data where also peaks might be strongly overlapping and we can't just select one wavelength. So this again, multivariate analysis comes at rescue here. Or when we want to know why some chemicals are having higher response in liquid chromatography mass spectrometry. Some chemicals are really hard to detect, their detection limits are very high. We need very high concentrations to detect them. But other chemicals have very low detection limits. So we need very little of the chemical to be detected. So what are the properties of the analyte? Or does it also depend on what kind of a liquid chromatography system we use? Again, we have very many parameters that are affecting this system, and we need to take them all into account. So it becomes a multivariate analysis. Sometimes we need to know what is a pH of a system. For example, when you are using liquid chromatography, we are mixing in reverse phase chromatography all the time a water phase, which contains a buffer, with an organic modifier. But organic modifiers affect the pH. So what is the end pH and how does this influence ionizability of the chemicals in the system? Again, there are very many variables that are, very many parameters that are affecting this. Or when we want to estimate the water content in building materials. So water content in building materials is regulated. It should not be too high to have a good quality, but how to measure that? One possibility is to use near IR spectra. And similarly to IR spectra in the kaolinite case, water signals in the near IR spectrum is also very complicated, and there are many overlaps with the peaks from building materials themselves. So it's a complicated task, multiple wavelengths that need to be taken into account. Or if we want to predict extractability, solubility of our analytes, what to use to dissolve our analyte, we need to take into account the analyte properties, which can be described with very many different parameters, such as log P, acid-base properties, and so on, as well as the solvent itself. How polar is the solvent? Does the solvent give hydrogen bonds? What's the dielectric constant? What's the viscosity? So on. So multiple properties again. Or when we are using ion mobility, then we want to know to which chemical our peak corresponds to if we are using ion mobility to determine the structure of the chemical. Or if we want to know the conformer, we want to know, okay, which conformer has the CCS values, the collision cross-section that we actually observe on the instrument. So again, we need to be able to somehow predict and then as well as understand why this is the collision cross-section for a specific structure that we are seeing. So these are just a couple of small examples where we have a lot of inputs that need to be taken into account to predict one output. And obviously, we can't do this with one at a time statistics. So we need multivariate analysis that we are going to use here as well. And to do this multivariate analysis, we are not going to do them on paper and pen, but because of the high dimensionality of the data, we are going to use computers, of course. So today, this is all done with programming languages such as R or Python. And as in the previous parts of the course, we are using R here. So before we can actually go on, I would just like to clarify a bit about the terms that we are using. So the inputs, the properties that we use to model something, they can be also called predictors, independent variables, features, or descriptors. And I am primarily using features or descriptors in my talk, and I know I'm changing between them. I'm afraid I'm not able to stick to just one term here, naturally speaking both of them. So I'm sorry for that, and just try to bear with me. These are also the two terms which you most often see in the literature. So what you hear here is also representative to what is in the literature used. So if we, for example, talk about predicting chromatographic retention time, then these descriptors or features are, for example, log P of the analyte, the acid-base properties of the analyte, its polarizability, but also solvent P, mobile phase pH, organic modifier type in the mobile phase, and so on and so on. And what we are predicting, so in this example, retention time, the output can also be called response or dependent variable. Terms independent variable and dependent variable are more classical multivariate analysis terms, and they're less used nowadays when we are increasingly going towards machine learning and deep learning in understanding this big data that we are collecting in analytical chemistry. And in addition to these two terms, there is also a functional form, and this is the mathematical conceptual relationship between the inputs and the outputs. So when we have a response that we are trying to describe y, and we have a number of different descriptors, x1 to xp, that can describe the y. Then the way they are related in our model, this is the functional form that we are using. And in this course, we are looking at the functional forms, which are multilinear regression, logistic regression, k-nearest neighbors, linear discriminant analysis, decision and regression trees, random forest, both regression and classification, as well as lasso regression and many others. And we will start with multilinear regression. You have actually the basics. We will be more by using this already existing knowledge that you have to build a general workflow of multivariate analysis. And many of these other functional forms are applicable both in the regression as well as in the classification task. And actually, in addition to this, we also have dimensionality reduction and clustering, where we will be looking at k-means and hierarchical clustering. And in dimensionality reduction, we look at the very classical principal component analysis, which are also largely used in analytical chemistry to understand the data and make best sense of it. So you now actually might ask, what she described just so many different functional forms. Why do we need all this? So when we go back to the different aims that we can have with our research, the predictions versus understanding, then when we are talking about understanding, then we are answering questions: which predictors, which descriptors are associated with the response? And also, what is the relationship? And sometimes it is not even so important that we get the best possible predictions out, but more that we understand why these predictions are made. So what is the functional form between the input and the output? And therefore, here the simpler models are preferred. For example, multilinear regression. And even within multilinear regression, rather the regressions which use less descriptors than more descriptors. It's just easier to grasp multilinear regression than, for example, random forest regression. And it's also easier to grasp if we have just 2 or 3 descriptors versus having 30 descriptors in our models. However, if our main aim is to do predictions, then we really want that the model would do as good predictions as possible. And therefore, we often need to sacrifice a bit on the understandability of the model, and we need to go for more complicated models, which are harder to grasp, but perform often better. So we had a couple of examples of cases where we have an input, which are very many different variables, and output, what we are predicting. And I have listed here a couple of more. And I would actually like to ask you to pause here and write yourself on a paper some more examples where you can imagine a multivariate analysis could be useful. So where you have inputs that you want to use, which are very many, and you have an output, what you want to predict, or between which output and input you want to understand the relationship.